This is problem 42 from chapter 18. And you can see their picture here, and I have started to draw my picture. We've got a positively charged plate up here and a negatively charged plate down here. So our E field lines would go from positive to negative. So if I draw my E field on here, it's going to go like that. And since this is an electron, it's going to experience a force in the opposite direction of the E field because it's an electron. Remember, E fields are defined for positive test charges. So we're going to have a force of the E field up, and that's our free body diagram. And that's it. Only one force acting on it. So when I look at this, right away I think this is going to have a lot in common with free fall problems, or if you want to call them projectile problems, that's fine. Because our force is staying the same, there's only one, and our acceleration is going to stay the same. And as soon as I realize that, I'm like, oh, motion equations can be used on this problem as well. So we've got motion equations and projectile ideas that we're going to be applying. Some additional information from the problem is that we have 2 centimeters for this distance. That'll be our displacement in the x direction. And we also have our displacement in the y direction, which, given in the problem, is 0.15 centimeters. So we've got this distance right here and this distance right here. So we have some additional information. In the x direction, I don't know what the acceleration is. In the y direction, I don't know what the acceleration is yet. But in the x, if I sum forces, there aren't any, so I'm going to get 0. So again, similar to projectile problems, I'm thinking that I can use this, which I can. It's thrown or shot horizontally at 7 times 10 to the 6 meters per second. And since it's fired horizontally, that velocity is on the x. And of course, we have no acceleration, so our velocity in the x will stay the same, but our velocity in the y will change because we have some acceleration due to this force. Now let's actually see what the heck they're asking us to find. Gives us our dimensions. It says, assume that the electric field between the plates is uniform. We've already made that assumption. Find its magnitude. So we're looking for the strength of the E field. So working backwards a little bit here, I'm going to say E equals F over Q naught. So I'm looking for the force. I don't have anything up here directly yet about force, so I'm going to expand out force to mass times net acceleration. And now we can start to see how we can get there. We know it's an electron, and we know, therefore, the charge here and the mass, because those are given on your table of information, or they're things you can look up. What we don't know yet is the acceleration, but all the similarities to projectile problems, I think I can find this acceleration in the y direction. I think that's something that I can find. Okay, so let's go ahead and start listing our variables like you might by starting in the y direction, and then we're going to get stuck. So y minus y naught, acceleration, initial velocity in the y, time, and v final in the y. V initial in the y is 0 because it's fired horizontally. This was my v initial. There is no y component, so 0. Acceleration in the y, that's what I'm trying to get to, so I can solve for E field. Displacement in the y, if I look at my picture, it starts here and goes up. We'll go ahead and call up positive 0.15. Let me double check that number. Yeah, 0.15 centimeters. I'll go ahead and use scientific notation. So 0.15 times 10 to the negative second meters. And again, if you don't remember your prefixes, you can look them up on your table of your table of info, sent to 10 to the negative 2. Or you can just move the decimal place over for one like this. That's okay as well. And we don't know time, and we don't know v final in the y. You might be tempted to call this 0, but no. In the y direction, as it goes by this point here, let me look at their picture. Yep. As it goes by this point here, it's going to be moving very, very fast in the y direction, so that is not 0. So we're stuck. Well, if we've looked at the y direction and we're stuck, let's look at the x direction. Typically, we wouldn't be stuck here, but we are. So let's go ahead and look at the x direction, and this is all that we have going on. And it just so happens that we have displacement in the x. And this velocity, because it's fired horizontally, is entirely in the x direction. So this is my velocity in the x. That's what the value is. Plug and chug up here. So I'll use scientific notation again. So 2 times 10 to the negative second meters equals Vx, which is 7 times 10 to the 6 meters per second. And then I know this is going to be really tough to see, but I'm multiplying there by time. Okay, I'll put parentheses. So Vx and t. This is good news. We have time from the x direction. Rarely does that happen. You have to be given the distance in the x and Vx, but that's what they gave us. So let's be happy about it. 2 times 10 to the negative second. I could do this in my head, but I'm not going to. I don't know why, but oh no, I couldn't do that in my head. I thought it was going to work out nicer and neat. and then that. Okay, so we got 2 times 10 to the negative second, or 0.02, yeah, divided by 7 times 10 to the 6th. So our time is very, very short, and that's fine. So 2.86 times 10 to the negative 9th seconds. And hopefully I did my math right there. If we don't get the right answer, we'll come back and check this work here to see if I plugged something in wrong. Go down here. Now I know 3 things, so I can pick my equation, and I believe it'll be this one, v naught t plus 1/2 a t squared. So just from the motion equations. So 0.15 times 10 to the negative second meters. Initial velocity is 0, so that goes away. Equals 1/2 a times that time squared. So 2.86 times 10 to the negative 9th seconds. So same number I had up here, a little bit more legible. And now let's solve for a. Again, grab the calculator real quick. So 0.15 divided by, or excuse me, don't worry about how I'm doing this, multiplied by 2, and then dividing by however you get the order of operations to work out on your calculator. 2.86 times 10 to the negative 9th. Insert and squared. And I'm getting acceleration of some huge value, 3.67 times 10 to the 14th, and that's okay. It's not like we're maintaining this acceleration for very long, so don't worry about going faster than the speed of light or anything like that. This can be, and often will be, for electrons or charges moving through E-fields, really big values. Okay? So that is reasonable, I think. And now I can go back, and I think I can solve for E-field, and we'll find out if we did this right or not. So we've got our mass of an electron, which I don't have my table info, so I'm going to actually look at the key. Sorry. Where's the mass of an electron? Eventually they plug it in here. I just need a mass. There we go. So 9.11 times 10 to the negative 31st kilograms. And again, you can look that up on your table of info. I just didn't have one handy. Over the charge of an electron, which I do know, 1.60 times 10 to the negative 19th coulombs, times our acceleration, which is 3.67 times 10 to the 14th meters per second squared. And let's see if we end up, I'm not going to have room here, so I'm going to write this answer down here. I'm not going to have room up there for that. So plugging in all these numbers, we will hopefully get, what'd they get? They got about 2 something times 10 to the third. Let's see if we get that. So that number I had earlier times 9.11 times 10 to the negative 31st divided by an electron's charge, 1.6 times 10. And I'm getting, this is what I'm getting without scientific notation, so 2088.3, and obviously no sig figs there. And they got 2.09 times 10 to the third newtons per coulomb. And I believe these are equivalent. 1, 2, 3, yeah. So I'm getting 2.08. Actually, if I round, I'm getting 2.09 times 10 to the third. So that is correct. Okay, so this work up here is perfectly fine. Section this off a little bit in case you want to pause and look. This part here in the middle, this is what I did at the end. Okay, I kind of figured out where I was going. I worked backwards from E-field just to make sure I'd solve for everything. But all of these numbers I plugged in at the end. So I looked at the X direction, I looked at the Y direction, projectile problem stuff, used the X direction to get time, listed my 5 variables for the Y, used that information to get acceleration in the Y, which is the acceleration due to the E-field force, and then I went back and tied the force, which is ma, to get the E-field. So our mass of our electron times the acceleration we got from our motion equation stuff divided by the charge of one electron. This combines projectile problem stuff with E-field stuff. If you have additional questions, feel free to stop by.